Great, thank you, Nick. Thank you very much for the invitation. It's a real pleasure to be here virtually and to have the opportunity to tell you about some things that I've been thinking about over the course of the last 5 years or so, on and off. What I'll be doing is hopefully covering a couple of what I think are interesting philosophical aspects of the theory of cosmic inflation. I'm not going to assume that any of you have great familiarity with the theory, and so I'll go through some of the rudiments of it as I'm talking about these philosophical aspects as well. Okay. Do you see the second slide now, Nick, just to check? Yeah? Yeah, great, okay. So what I want to do is I want to try and put into context parts of a dispute in cosmology about the very early universe, and in particular about the theory of cosmic inflation. So inflation is extremely popular amongst cosmologists, and there's a large theoretical contingent, and there's also an experimental contingent working on cosmological experiments, which have dedicated teams that look at inflation itself. Most recently, you would have heard of the Planck collaboration, who came out with a bunch of papers, one of which was solely on inflation and testing models of inflation. But it happens to be the case that there's a small but influential band of physicists, as I say here, who contend, in light of some of these results, that inflation has grown increasingly implausible. And so there was a debate in 2013-14 in the literature between two sides, as it were. Annie Aegis, Paul Steinhardt, and Avi Loeb. On the one hand, it's in 2013, and then a response to this particular paper, which outlines some of these problems with inflation, was authored by Alan Guth, David Kaiser, and Yasunori Nomura in 2014. And there was another paper by Andre Linde as well. And then this debate resurfaced primarily as a result in 2017 of a paper in Scientific American, which is written by the same set of three authors that I mentioned originally. And then a response to that particular paper came along as well by Guth, Kaiser, Linde, Nomura, and there were 29 other signatories who signed on to this particular response. So red here is arguing that inflation is problematic, and green is defending inflation. Okay, so so what I want to do is I want to try and clarify what this debate was about, and philosophically interpret some aspects of this dispute, where I focus on two main charges that came up in this debate. And these two charges are related to the following two questions. The first question is, how finely tuned is inflation? And I refer to this, the problem that results from thinking about this particular question, as the initial conditions problem for inflation. And then the second question is whether inflation describes only the structure we see, or more than the structure that we see. So inflation famously, and I'll say a little bit more about this in a second, describes initial density perturbations in the universe, which then are putatively thought to grow into large-scale structure that we see today. There's a complicated, beautiful, complicated story, which takes you from the initial density perturbation to large-scale structure. But the idea is that inflation can account for large-scale structure today by seeding that structure primordially. But the question arises whether inflation just describes large-scale structure, or whether, in fact, is able to describe stuff that goes beyond what our observable horizon. The answer to that question is generically yes. It does make claims about structures beyond our observable horizon. Namely, it, as some of you may know, purports that there exists, in fact, a multiverse where we are just one domain in this multiverse, or one universe in this multiverse. And there is a particular problem that you could imagine arises in conjunction with this. Namely, how do we go about testing such a theory which gives rise to such a structure? So I'll go into this in a little bit more detail as well. There are two one of these problems is immediate, as it were. I think the question of fine-tuning of cosmic inflation is something that we can address today. I think we have at least the rudiments of the tools to address this problem today. Whereas the multiverse problem is, from one point of view, lies in the future. we don't quite have the theory of the multiverse. I mean, there are hints that the multiverse exists. You need to extend the theory of inflation to very high energy scales to probe the kinds of effects that give rise to a multiverse. And so there is a sort of speculative theoretical component, but I think in conjunction with that, one could still, so I should say despite that, one can still ask interesting questions about confirmation of any such theory that might arise in the future. And some of those questions are what I'm going to get into today. So these are not the only problems with inflation or the only bones of contention, as it were. There are many others, like 3 or 4, I would say, categories of problems that one could identify. And they are highlighted in this paper by Chowdhury and others from 2019. So if you're interested in a sort of a wide-ranging discussion of the various problems that exist, I would recommend that you take a look at this paper. What I'm going to talk about comes from part of it exists in this paper in the bottom as well, where I discuss one other problem with inflation, which I think is a third problem that really is at stake in the dispute, in the debate that I mentioned on the last slide. Okay. So, as you may know, cosmic inflation, one of its motivations was as a solution to fine-tuning problems. And the issue was the following, that by the early 1970s, a standard Big Bang model of cosmology, this is dubbed standard by Weinberg in the 70s, this standard model had been established, and it described the universe from just after the putative Big Bang singularity. But it faced some major problems. And the problems were the following: the model stated, but it didn't tell you why certain features of the universe, as we see them today, are the way they are. So the universe today is extremely flat. So it's very Euclidean, but flatness is very special. It's a very special state according to the standard Big Bang model of cosmology in the 1970s. And the standard Big Bang model can account for this, but it doesn't necessarily provide a great explanation for it. The other feature, the other fine-tuning problem that exists with the standard Big Bang model is this, is what I've called uniform here. So right here, namely the cosmic microwave background radiation today is almost uniform in all directions. So the temperature is essentially the same. Whether you look in this direction or this direction, the temperature is very similar, despite it being the fact that in the context of the standard Big Bang model, radiation that comes from here and radiation that comes from here is in fact causally disconnected. So patches in the sky that are separated by order of degrees or more have not in fact been in causal contact with one another according to the standard model. And so there is a sense in which the Big Bang model can account for this, but it doesn't necessarily explain it, or the explanation that it gives isn't a particularly good one. So in 1980, then, Alan Guth submitted a paper. It was published in early 1981, which claimed that, in fact, just after the Big Bang singularity, the universe, the observable universe, underwent accelerating expansion, and it increased in size by a huge factor of e to the 60. So this factor here refers to 60 e-folds of inflation. 60 e-folds refers in principle to the scale factor, which I'll talk about in a moment. So exactly how this expansion is implemented in a particular cosmological model, I'll talk about. But the idea is that the universe expanded by lot, space expanded by lot. This resolves the flatness and uniform problem. And it resolves the flatness problem because essentially it takes space and stretches it out. And so any inhomogeneities that might have existed in space get stretched out so that things today, to us, look locally flat, as it were, although things may be varying wildly on much larger scales. Locally, things look flat. And it solves the uniformity problem because essentially it says what we're looking at today is a causally connected patch. It is possible that the patch that we're looking at today, the observable universe, very early on, things were in causal contact, equilibration could have happened in such a way that it wouldn't be surprising that the temperature that we see in cosmic microwave background radiation, looking in various directions of the sky, is in fact very similar. So these are some of the motivations for inflation, but inflation goes further than this, and perhaps one of the reasons why people are very excited about it is really the second point that I make here, that by the time inflation is over, as I mentioned right at the beginning, there are small differences in the density, in the sort of energy density across space. And these differences can account then for these small variations in the cosmic microwave background as a function of direction in the sky, namely these anisotropies. So things are pretty much uniform everywhere, except but they're a little bit different. They're slightly anisotropic. So inflation can account for this and account for the statistics, as it were, of the anisotropy. So inflation doesn't tell you that that direction is going to be warmer than that direction, but it tells you what the statistics of the distribution of the temperature fluctuations will be, and it can account for the observable statistics of the fluctuation in the temperature. So the idea is then it provides, by virtue of these density differences very early on, it provides a mechanism to account for structure in the universe. So it can account for galaxies and stars and planets and us eventually. This can also be seen as a solution to a fine-tuning problem for the standard Big Bang moment cosmology in the 1970s. Could also, in principle, account for these small differences in the density, but it has to put them in by hand. Whereas inflation is providing you with a dynamical mechanism. In fact, it's sort of a theory of quantum field theory on curved spacetime, which allows you to account for these density differences. Okay. So this is what I want to do today. I want to, as I say, put a lot of this stuff in context and provide some conceptual context for some of these issues. And so I want to talk a little bit about fine-tuning at the beginning. And then I want to describe the flatness problem. So for those of you who haven't seen this before, it'll provide you with some context of what exactly the problem looks like, how it is inflation goes about solving it. And then I'll talk about how one could realize inflation. So there'll be a slight interlude where I talk about some technical issues to familiarize you with how it is that cosmologists think about, or at least one way of implementing inflation. And then I'll talk about these two problems in turn. So in particular, I'll talk about the initial conditions problem, how it has been addressed and how it could be addressed. And as part of this, I'll highlight some of the work that I've done recently with David Kaiser, which looks at this particular problem. And then I'll talk about the multiverse problem probably in the second half of this. And in particular, I want to highlight the fact that, as I mentioned, the multiverse problem is really a problem. The particular multiverse problem I have in mind is a problem of confirmation. How do we go about confirming the theory that gives rise, or a theory that gives rise to a multiverse? And what I want to point out is that there really are three sub-problems, each fascinating, each open, each hard to some degree, that comprise the multiverse problem. And so I'll go through each one of these in turn. Okay. So here's some background. So on fine-tuning, this is Bill Bialik, who's a distinguished voice in theoretical biophysics and in physics, in a book called Searching for Principles, which I should highly recommend if you're interested in biophysics at all, or theoretical neuroscience, or even phenomenological experimental aspects of these fields. I would highly recommend reading this book. Bill talks about fine-tuning in a way that is probably familiar to those of you who encountered fine-tuning before, and those of you who've worried about physics before. So he says, physics, especially theoretical physics, is a search for concise mathematical descriptions of nature. And the dirty laundry of this enterprise is that our mathematical descriptions of the world have parameters. If the predictions of the model are too sensitive to the exact values of the parameters, there is something vaguely unsatisfying about our claim to have explained things. So, so I have highlighted vaguely unsatisfying. He did not put them in pink in his book. And then he says, such strong parameter-dependent explanations are often called finely tuned. And this is the key point, we have grown to be suspicious of fine-tuning. Okay. So I'll come back to this quote in a minute. So here are some such finely tuned phenomena, and you may have your own favorite ones. You should feel free to chime in if you have one that is not listed here. So here is one. As I mentioned right at the outset, the Euclidean nature of spatial slices of our universe today is arguably finely tuned according to this standard Big Bang model of cosmology of the 1970s. Most strikingly, and life as we understand it is finely tuned according to the standard models of particle physics and cosmology. Here's an example from black holes. A state in which primordial black holes make up a significant fraction of the dark matter of our universe today is arguably also finely tuned according to various models that produce such black holes. So this is the idea that the dark matter that exists in the standard model of cosmology, the lambda CDM model of cosmology, lambda corresponds to the cosmological constant, CDM corresponds to cold dark matter. The contention is that maybe that cold dark matter is in fact comprised of primordial black holes. These are black holes that formed very, very early on in the universe. One particular mechanism that could give rise to primordial black holes is inflation. The idea, though, here in this particular context is that that particular scenario where primordial black holes make up a significant fraction of dark matter is a finely tuned phenomenon. Okay, and there are others. So proteins is another example where fine-tuning might arise. So you could just take the amino acids and randomly distribute them and you wouldn't get a functional protein. Proteins are sort of very specific combinations of these amino acids. There is some robustness. You could take a functional protein and you could make certain substitutions and still have a relatively functional protein, but that's different to randomly putting together the amino acids and hoping that you end up with something that's functional. There are two senses of fine-tuning that I just mentioned in that protein context that I want to probe a little bit more now. So what is a lack of fine-tuning? So you may have heard of really a cluster of related concepts that overlap with notions that you might have. So when you've heard of the notion of not finely tuned, you might have heard of words like stability, robustness, or naturalness. Maybe there are others. The claim that I want to promote here is that these do subtly differ from one another, but there is a common core that sits at the heart of each one of these concepts, which is the kind of thing that I'm going to be probing in thinking about fine-tuning. So stability, an example of stability is actually just the example that I gave. You might be able to pass this notion of invariance under substitution as a notion of stability, invariance under amino acid substitution. Or you might want to think of it as robustness. We can come back to that. So a more common notion of stability arises in, for example, the Einstein static universe, a universe which is spherical, positive curvature, has a cosmological constant and matter. The cosmological constant and matter have to be balanced very finely. They have to match in a particular way. If you increase the amount of matter by a little bit, or you decrease the amount of matter by a little bit relative to that equilibrium value, the universe will either contract or expand forever, and contract forever, as it were, or expand forever. So this particular state, this steady state, is unstable. Robustness has added features, and it arises in biology. I think that the real difference comes across when we think about robustness in the context of biology. So here is a paper by, here's a quote from a paper by Kitano, where robustness has features such as parameter insensitivity, which is sort of the notion of stability that I talked about, but also adaptation, so the ability to cope with environmental changes is a biological notion that comprises robustness. And then there's another aspect of this, namely graceful degradation. So the slow degradation of a system's functions after damage rather than catastrophic failure. Okay, so you could think of the Einstein static universe as slowly degrading, if you wish, but this is not quite the notion here. There's sort of a functional notion that plays itself out in the actual world. that comes into play when thinking about robustness in the context of biology. And then you will have heard of naturalness in the context of particle physics. Porter Williams has a very nice paper on this, which I would recommend that you look at if you're interested in this. And naturalness is defined, or there is an important feature of naturalness which is described in the following way. Namely, there's a naturalness arises when you have a prohibition of sensitive correlations between widely separated energy scales. So a good example of a problem where you require correlations between widely separated energy scales is that of the cosmological constant problem, where you know that the experimental value of the cosmological constant is extremely small. However, if you think of the cosmological constant as given by vacuum fluctuations in quantum field theory, the value is in fact, value you end up with is very large, and the ratio of those two values is huge, right? Depending on the units that you use, order of 10 to the 100 or so. So you need those to balance each other out in some way to end up with an explanation for how it is that the observed value that we see is so much smaller than the value that is predicted by quantum field theory. So the point is that, you know, there are these kinds of concepts are different. However, there is a common feature, and the common feature is the following: that there is so I'm going to put it in general terms, sort of necessarily so to capture what is common amongst things which are distinct. That the common feature is that there's an invariance or a preservation of some phenomenon. Something persists, something keeps happening, and this invariance or preservation occurs in the face of changes of a certain type. Okay. So let me try and make that, I don't know if this is more obscure or less obscure, but I'm going to try and make it a little clearer. Here is one way to characterize fine-tuning, taking this kernel of the idea that I think sits in the center of that Venn diagram, these various ways of thinking about fine-tuning. So here's the characterization. Sorry, I need to close this. So fine-tuning of some phenomenon, so I'm going to refer to phenomena as finely tuned, as described by some model M, it goes as follows: if circumstances in M were a little different, F would change significantly. So if the circumstances in the model were to change just by a little bit, the phenomenon, the thing that I'm actually interested in, would somehow evaporate, would change markedly. And so in trying to make this precise, you run into the problem associated with describing fine-tuning, or the various problems that people run into when they think about fine-tuning. One is, what circumstances are you in fact talking about when you're talking about a particular model? If you're focusing on dynamical systems in physics, these are relatively straightforward to identify. So equations of motion for dynamical variables, initial conditions for those dynamical variables, and parameters that enter into those equations. These are parameters that are not fixed by the theory, but you need to fix by hand to get the theory to agree with observables. So these are, you know, in a broad stroke, the kinds of circumstances that you run into when you're dealing with dynamical systems in particular. The real controversy of fine-tuning comes in when you think about this notion of what it is that you mean by a little different or change significantly. There's some notion of a measure here, size, which is not specified, which you need to specify, which when you do specify, tends to cause problems. So this is the least tractable aspect of the broad characterization. And there's one other important aspect of this, and that is the phenomena F. Which phenomena should you be focusing on? Which phenomena do we judge as being important, essentially? So, you know, as I say here, you know, you are finely tuned. You, specifically you, are finely tuned. Things have to turn out just so, so that you arose. But that's unfortunately not the most exciting thing from the point of view of judging the finely tuned nature of the standard model of particle physics and cosmology. There is something else that we need to point to, some other salient phenomenon of which you are you're a member, a class of which you are a member, that is in fact important here. And some of the things I've seen thrown around are ideas such as complexity, life, right, is tricky to define. We'll come back to this point when we talk about the multiverse problem. But the general issue is that one needs to try and figure out what the salient phenomena have to be. And as you'll see in when I describe some of the more technical work that I've been working on, I seem to endorse, at least for now, a pragmatic approach that gleans the salient phenomena from the context. Namely, you can tell what it is. You sort of have to stare at it hard enough. This is a feasible way of trying to come up with figuring out what salient phenomena happen to be, but it can work in certain circumstances, and so it shouldn't necessarily be cast aside, because this method shouldn't be cast aside just because it's not somehow rigorous. Okay, this is sort of one thing that sits in the background of what I'll be discussing. Okay, so the next question that arises then is, what is it that is problematic about salient phenomena that are finely tuned, right? What is the problem here? As I mentioned at the beginning, the standard Big Bang model of cosmology can't account for all those things. It can't account for flatness. It can't account for uniformity. It can't account for the differences in density in density that you need to seed large-scale structure. But somehow there's something problematic about it. And here is a response to the question, what is problematic about salient phenomena that are finely tuned? Namely, really nothing. You can't unambiguously assign fine tuning. It's sort of a denial of the premise of the question. And the one aspect of something that guides some of the work that I'll be talking about is the following, namely that if you remain agnostic about the possibility of fine tuning, this is just the wrong stance to take. It might not be important, but it could work out to be important. And so under this kind of idea, one can and should look to assess degrees of fine tuning. So this is the rest of the quote from Bill earlier. So he says, experience suggests that if parameters need to be set to precise or somehow unnatural values, then we are missing something in our mathematical description of nature. And part of this outlook is the idea that fine-tuning is in fact, and can be, doesn't necessarily have to be, a spur to theory or model development. So when you notice fine-tuning, this is something that even if you noticing that fine-tuning isn't super rigorous, it's still possible that there is a better theory that underlies the situation, and that the fact of the existence of that better theory is pointed out by the fact of the existence of fine-tuning. So here's an example. Ptolemy. I mean, I put question marks here because they're questions. I'm not necessarily stating that this is a fact, but the models of the universe, of the solar system, of the universe as a whole, of Ptolemy compared to Kepler, one could argue that Ptolemy is significantly more finely tuned than Kepler. One could also make the same claim about the comparison between Copernicus and Kepler. Ptolemy and Copernicus, there's a question there as to whether one is more complicated than the other, or whether they're in fact similar in terms of how complicated they are and maybe how finely tuned they happen to be. So Steven Weinberg discusses this issue of fine tuning in the context of Ptolemy's models, and you can read about it. I think the book is called To Explain the World. And the idea is that certain things have to be fixed to be very precise. For example, for Mars, as an example, you have, so Ptolemy's model is that you have the planet going around an epicycle, and the center of that epicycle goes around a deferent. So in the simplest model, there's no eccentric. Let's just put the Earth right at the center. Then one kind of fine tuning that he points out is that the line between the Earth and the Sun always has to be parallel to the line between the center of the epicycle and the planet, right? Those two angles could be anywhere, could be anything, but they have to be parallel for all time. And then you also have to fix the rate at which these planets go around, which Mars in particular, in this particular example, goes around its epicycle, and the rate at which the center of the epicycle goes around the Earth. Okay, so and then as I've claimed that people have claimed the Big Bang model in the 1970s to cosmic inflation is an example of a situation which putatively reduces fine-tuning in the context of the Big Bang model. There is a question whether it then introduces the notion or a problem of fine-tuning in the context of cosmic inflation. This is, the initial conditions problem that in the context of cosmic inflation. I'll be talking about that in a little more detail. Okay, so here's another response. Nothing. There's nothing problematic about salient finely tuned phenomena. Think about chaos. Chaos is a theory. It describes certain phenomena, and it is extremely finely tuned. And in the sense that if I were to change the initial conditions, say, take a double pendulum, the simplest example that you may have seen in the physics class, you change the initial conditions by a little bit, the ensuing pattern of the double pendulum's trajectory in space-time is completely different, okay? So if you take any particular trajectory then as being a phenomenon, salient phenomenon, you could question each one of these assumptions, then each one of those, so that particular phenomenon is finely tuned. Just by virtue of changing the initial conditions, things change dramatically. And in a sense, I mean, I'd be interested to hear people's thoughts on this at some point. There's a sense in which one may need to set aside chaos in thinking about fine-tuning. This doesn't mean that there aren't things like distinctively good explanations that are based on the theory of chaos. It depends on what you mean by a good explanation, but this notion of fine-tuning seems embedded in the, at least ostensibly, in the theory. All right. And then the final response is that there is another way of saying nothing in particular is problematic about salient finely tuned phenomena, is that, as I said, finely tuned phenomena aren't empirically inadequate. The standard Big Bang model of cosmology in the 1970s can account for flatness, uniformity, and density differences. It's not empirically inadequate. It just seems to do it in a way that's suspicious. That's the idea. A sort of counter response to this is that, sure, these finely tuned models are not empirically inadequate, but it seems fine-tuning somehow jarring enough to raise the question of whether there's a less finely tuned account available. And if it's really true that there are interesting examples from the history of science in which, I mean, even from a post hoc fashion, you go back and you look and you notice that, oh, fine-tuning somehow decreases as a result of the development of this theory, this adds some weight to some degree to the claim that this, you should worry, the fact that it's jarring is telling you something interesting. Okay, so maybe I should stop there just briefly to see if there's any questions, because I'm going to now talk about the flatness problem.
I didn't see any come up in the chat yet, but if people do have questions, this is a good point to sort of jump in. Oh, Jeremy, you have a question?
Yeah, sure. So I'll just make this quick. I thought this discussion of how fine-tuning is motivated is really interesting, and I guess I'm curious to see if you'd agree with the following sort of claim. The attitude that you take towards fine-tuning is going to kind of depend on what sort of theoretical virtue you think it is meaning to achieve. So I take it that it's supposed to add some sort of explanatory power to our theories, if we can resolve a fine-tuning worry. But I'm wondering if you think that we ought to just approach it sort of cautiously as one possible way to add explanatory power in theories where there aren't many options open to us, like early universe cosmology, or if you think that indeed it is better motivated by other concerns and other virtues as well, like, for example, conservativeness, and that fine-tuning arguments have been deployed before successfully in the sense that Weinberg is talking about. If the latter is the case, then I think that worries about just how well Weinberg's reconstruction works become more pressing, in the sense that it seems like there's you could possibly worry about the Whiggishness of that reading, and if agents were really having fine-tuning concerns in mind when they were developing successive theories.
Yeah, no, great, thanks for that. So I think there's certainly an element to which the theoretical virtue that's being compromised, one can interpret the theoretical virtue that's being compromised by the existence of fine-tuning as that of exactly what you say, explanatory power or depth. And that there is, at least that is in play for certain kinds of explanation. This particular claim that I just mentioned doesn't quite work when you think about something like chaos, because you could argue that there are other ways of thinking about explanatory depth that don't quite relate to fine-tuning, for which chaos is, providing still a deep explanation, right? If it can, so unification type ways of thinking about explanation will take the fact that you can explain the weather and the double pendulum using a similar kind of theoretical structure and say, look, that's a good explanation. So there's a caveat to the claim that there's that kind of caveat to the claim that the explanatory depth or power is something that's being compromised by the existence of fine-tuning. Right, and then to this sort of post hoc reconstruction, I do worry about that, right? I do worry about it. So this, maybe I don't quite know how to address, but the sociology of the way inflation came about is a good example of the kind of worry that you might have. So if one was to study the kinds of worries that people had about fine-tuning and how they led to the development of inflation, I think this would be a good case study for the kind of issue that you have in mind. It's not something I've done, but it may exist. There may be something recent on this. Does that answer your question? Yeah.
Oh, absolutely. Yeah, thanks.
Okay. Okay, so if there's nothing else, maybe
Niels, do you have a question? I see your mic's on.
I'm sorry.
Yeah, no, great. Yeah, let's move on then. But people can either put their hands up and I'll keep an eye on that and, butt in if people have questions or put them in chat and yeah.
Okay, great. Okay, so to the flatness problem, so this is my opportunity just to introduce some notation to help with what's going to come later, and to introduce you to the problem itself if you haven't seen this before. So the geometry of space, as I said, so this is space on large scales. So clearly, right, things aren't flat on this. I mean, so things aren't absolutely uniform on the smallest scales, but space on larger scales is described by three-dimensional Euclidean space. And here is how one can think about the flatness problem in the context of the standard Big Bang model. So here's the Friedmann, Lemaitre, Robertson, Walker metric for space-time. I've set the speed of light to be unity. And so you have the usual metric form where you have a time component together with a spatial component. The spatial component is given by this here, and it consists of a piece, namely a scale factor, which is A of t, which tells you how your spatial slices, how big they are in a sense. So this particular factor, if you set k to be 0, for example, this is just Euclidean three-dimensional space in polar coordinates. And when k is positive, you get positively curved three-dimensional space, and when k is negative, you get negatively curved three-dimensional space. So the point is, when k is equal to 0, that is when spatial slices are Euclidean. And we can analyze this system in the context of general relativity by assuming there is some sort of matter content, which also exists, and the matter content is going to be specified by a mass density together with a pressure. and they are in principle separate from one another, but it is useful to combine them. It's a way to actually represent how matter, the kinds of pressures and that arise for actual matter in the universe. So this equation of state, as it's known, relates the pressure to the energy density in this simple way. It's an assumption. And if you put this then into Einstein's field equations, you get the following two equations. So, so this equation is telling you the following. So H is what's known as the Hubble expansion rate. This is a term that goes back to Alan Guth. Sometimes people call this the Hubble parameter or the Hubble constant. It is neither a constant nor a parameter. And so, one can, so I'll call it the Hubble expansion rate. This is telling you, this particular first equation, the Friedmann equation, FR1, is telling you how that rate depends on rho, which is the mass density, and there's another term for the curvature, which arises really on the left-hand side, and I moved it to the right-hand side. So you have an equation here which relates matter to geometrical degrees of freedom, as you know, occurs in the context of Einstein's theory of general relativity. There's a second equation which tells you how the acceleration of the scale factor changes with time and how it depends on things like the mass density and the pressure. And then there's also finally an equation of conservation. It is an equation of conservation of stress energy, and it tells you essentially how, it's another equation that tells you how the matter content couples to, through H here, how it couples to geometry. These are not three independent equations. You can derive, for example, this second one from the first one and the third one. So you just have really two independent equations. Okay, so here's how you can think about the flatness problem. So consider just the first Friedmann equation, the first Einstein equation, and I'll drop explicit time dependencies for now. If you divide through by h squared, then you end up with the following expression. The thing in blue here, the inverse of that thing in blue, that blue box, is known as the critical density. And it's the density such that if the mass density of the background matter or the fluid were to take that value, that would force K to be 0, right? So if rho took the value rho C, then that would force K to be 0. Okay. So, so this quantity omega is known as it's a dimensionless density parameter, and it monitors, by virtue of this first Friedmann equation, it monitors the geometry of these spatial slices, right? So you can see, just by definition, that omega equals 1 corresponds to the case where spatial slices are Euclidean. So people often talk about omega in cosmology, and this is one reason why they do it, because it's a signpost to the geometry. Okay, so you can then show by using the first Friedmann equation, the second Friedmann equation, that the following holds. So here I've taken the derivative of this dimensionless density parameter with respect to the logarithm of A. This is a new, I don't know if you see, do you see that when I highlight it? Maybe not. So that you do. Okay, so this logarithm of A is another time parameter, right? Which you can, I mean, if A tells you sort of how big the spatial sections are, and if A is increasing with time, as it will in an expanding universe, it can be thought of as a time parameter. And then the logarithm, a monotonically increasing function of that parameter, can also be thought of as a time parameter. So I can just think of log A as time. Okay, so it's no big deal. So, so the change in rate of this density parameter with time looks like this, right? It's a straightforward calculation. Notice immediately that omega equals 1 happens to be a solution, right? If I put omega 1 to the right-hand side, I get 0, and to the left-hand side, I also get 0. So, what this tells you is that in the standard Big Bang model of cosmology of the 1970s, you can explain flatness. You've just got to set, you know, omega to be 1 or close to 1. You have that freedom. You can do it. Here's the problem, though. If you consider a small perturbation about the solution, so this is this notion of stability that we were talking about earlier. If you think about a small perturbation about the solution, so let delta be small, I substitute this back into this original equation, then you can look at the change in rates of you can look at how this perturbation evolves with time. okay? So it's straightforward calculation to order delta to the smallest order in small quantities here, sorry, I should say to first order in small quantities here, you get the following expression that d delta by d log a is proportional to delta, which should tell you immediately that that this holds, right? So you divide through by delta, as it were, and you integrate. And you find that delta is proportional to a to the power of 1 plus 3w. Okay, so if 1 plus 3w is less than 0, then as a increases, delta is going to go to 0. So if I take, what this tells you is that if I take the original original flat solution, I perturb by a little bit, that perturbation dies away. If 1 plus 3w is greater than 0, then as a increases, delta is increasing. And so the kinds of matter that you expect in the standard model, Big Bang model of cosmology, namely what's known as dust, which is pressureless matter, so P is 0, so W is 0, and radiation, which also satisfies this particular expression. If you just had a universe with these kinds of matter in it, then this perturbation would grow. And so you would have to set this density parameter to be very close to unity at the outset, at where the outset corresponds to some chosen initial time, to be as close to unity as it is today. How close to unity is it today? This close to unity, right? That's pretty close. And how close would you need to set it early on in the universe? Well, it depends on exactly when it is that you ask. It depends on the chosen initial time. If the initial time is 1 second after the period of Big Bang singularity, then omega has to be close to 1 within 10 to the minus 18. And if you set the initial time earlier and earlier, all the way back to this 10 to the minus 34, which is roughly the time at which inflation is thought to have occurred, then omega has to be very close to 1 to this degree, right? So within 10 to the minus 52. And so this is the kind of claim that underwrites, this is the kind of calculation that underwrites the claim that the flatness, that flatness is finely tuned according to the standard Big Bang model of the 1970s. Okay. So, the summary, change omega by just a little bit in the standard model, and you get something that's going to be very different to omega is 1 today. It won't look like this. It won't agree with this, with the recent Planck result. All right. So how do you solve the flatness problem? No problem, right? Just stare at Einstein's equation. Notice that I can write the deviation of omega from unity in the following way. And so all I need to posit is I need to posit a period of time when this thing decreases with time. When that, if I can,
sorry,
yeah.
Can you just remind, on the previous slide, just remind me what W was? Was that what appeared in the equation of state?
It's the equation of state, exactly. So it's the equation of state. Sorry, I should say, as an example of what that means, people talk about non-relativistic matter. Non-relativistic matter, so matter moving sort of lugubriously, slowly, is, if you imagine erecting a screen, say here, and you're looking at matter that's sort of moving super slowly, then the pressure that this particular screen is going to be feeling as a result of this matter is going to be basically 0. So W then equals 0 in this case. There's an energy density, but the pressure happens to vanish. So, so that's dust. Okay, and one can compute a similar quantity for radiation. Okay. All right. So we were in the process of solving the standard this flatness problem. As I mentioned, if I have a period in which this quantity AH inverse decreases, then I can drive this density parameter towards unity. And that is sort of the heart of the inflation. That's one way to think of the heart of the inflationary solution. That you could start with a value of omega that's very far from unity. You just need a sufficient amount of time over which the geometry evolves in such a way that AH inverse is negative, is decreasing, and you can drive omega close to unity, and then you can let unity, and then you can let omega evolve in the usual standard way, such that it remains within the bounds that we see today. for omega, as mentioned, as I described in the other slide. Okay, so this is how people define, this is one way to define inflation. So you can define it as a period where the Hubble radius decreases, but there are other ways that you may have seen or will hear about, and I want to point them out just so that you're familiar with them. It also gives you some familiarity with the ways in which people work with inflation. So what I want is, I want a period, as I mentioned, where AH inverse is, the derivative of this is less than 0. It's decreasing with time. So you know that H is A dot over A, and A times A dot over A is A dot. And so you can very easily take the derivative of this quantity, and you can show by this first formula here that a decreasing Hubble radius is the same as an accelerating scale factor, right? So people talk about accelerated expansion. This is why they talk about accelerated expansion. Another way to think about it in the context of inflation. Here's another way to think about it. You can also think about inflation as a slowly varying Hubble expansion rate. So let me define this. Let's just define this quantity epsilon. Epsilon is minus h dot over h squared. How do I think about it as as a physical quantity? Well, it's sort of minus the fractional change in h per unit Hubble time. So per unit time, where time is measured in units of the Hubble time. So it's a fractional change in the Hubble expansion rate per unit Hubble time. As I say here, a simple calculation with this definition shows you the following expression, shows you that this is true, that d by dt of AH inverse is related to epsilon the following way. So, a negative or a decreasing AH inverse implies, and it's implied by an epsilon which is less than 1. So an epsilon's less than 1, accelerated expansion is occurring, inflation is occurring. Any deviation from unity, any large deviation from unity is being driven towards unity very early on in the universe, solving the flatness problem. Okay. Here's another way. People talk about quasi-de Sitter expansion as a way of describing inflation. And if you, in fact, if you set epsilon to 0 from above, you know that the definition of epsilon, actually, did I include it here? No. So the definition of epsilon is proportional. So it's minus h dot over h squared. As epsilon goes to 0, h dot goes to 0, which means that h is a constant. When h is a constant, I have a very simple differential equation to solve for the scale factor, right? Namely, a dot over a is a constant. And so, therefore, A is proportional to e to the ht, where h is a constant. This gives you exponential expansion. So inflation, you will have heard, is also referred to as accelerated expansion or exponential expansion. This is where the exponential comes from. Okay, so then one other way is that you could have you need a fluid with a sufficiently negative pressure, right? A strange kind of entity. But from the second Friedmann equation, from that acceleration equation, a double dot greater than 0 is implies and is implied by the pressure being less than negative 1/3 overall. So if you can find some sort of matter that behaves in this way, you're able to instigate inflation. Okay. And then there's one other way that I don't think I'm going to refer to later. So I may just skip this. But here are some ways this is true. And if you want more details about this, there's a lovely set of lecture notes by Daniel Baumann on cosmology, and he goes through these and inflation more generally, and I'd highly recommend them. Okay, so now I'm at this, I want to get to this interlude where we talk about how you in fact realize inflation. I just mentioned how you can describe inflation, define it as it were. Here's how cosmologists tend to at least talk about it in the simplest case. Okay, so the goal then, let me go back to this. The goal, I'm going to focus on this. So the goal is to try and construct some sort of matter degree of freedom which gives me a sufficiently negative pressure. So here is how you can do it with a single scalar field. So this is a hypothetical entity which can source inflation as I've defined inflation. So the action for a single scalar field, minimally coupled, as it were, to gravity, is given by the following equation. This is the Einstein-Hilbert term. This is a term which includes kinetic and gradient degrees of freedom. Gradient degrees of freedom meaning spatial derivatives of phi, potential term, which essentially tells you the kinds of forces that the field phi is subject to. So the features of this particular simplest realization of inflation are you have a field phi, which could varies in time and varies in space. It's a single scalar field, so there's not a vector, it's just one. There's just one field. It's known as the inflaton field. There's a potential term, which, as I mentioned, describes how describes in a sense the forces that this field is subject to. There is the sort of typical form for the kinetic degrees of freedom for the inflaton. Gravitation is encoded via the Einstein-Hilbert action. You could imagine adding other terms in this particular action. If you wanted to, they would be sort of non-standard gravitational degrees of freedom, although there are arguments that those kinds of terms should exist. But this is the simplest realization. And then there is minimal coupling, meaning there's no terms in this action which couples phi and r together. Okay, so this thing here is the usual single scalar field model of inflation. And it is not the only way that one can realize inflation. In fact, this particular fact here, namely that it's not the only way, is seen as a problem in that debate that I mentioned right at the beginning. One of the problems was that there's just too many ways in some sense. And we don't have any theoretical clues about how to reduce, or the theoretical clues that we have aren't sufficient to reduce the total number of ways to something that's more manageable. This is a charge that has been leveled at inflation in various places. You'll see it referred to. Okay, so what does this look like in terms of its equations of motion? Well, the simplest thing that we can do, as I mentioned, the simpleton field can vary over time and space. I can assume that the inflaton field is in fact homogeneous. So I imagine that in every single spatial slice, it takes the same value at every single point in space, but it can vary with time, right? So this is a way of mimicking a homogeneous universe. A standard calculation, as I say here, allows you to identify rho and p, namely the mass density and the pressure, and then the sort of balance between the kinetic degrees of freedom, which is what this is, and the potential allows me to relate p with rho. There is no way to relate these directly, but under certain assumptions, I can relate p and rho directly through something like an equation of state, which is kind of what I want to do eventually, because I want to get a pressure that's sufficiently negative relative to the energy density, right, to give me inflation. So if I simply substitute these particular expressions into the original equations, into the Friedmann equations and this continuity equation, I get what you see on the right-hand side here. So this is a direct substitution. Nothing fancy going on. Let's see how you get inflation. Okay, so note that in these equations here, I haven't in fact specified the form of the potential, right? I've just said that some potential exists. Once you do specify the potential, there are two free functions of time, and as I mentioned earlier, two independent equations, right? There are three equations here, only two of them independent. The two functions of time are phi of t and a of t, which sits here. Phi is the matter content, a is the geometrical content, and Einstein's equations relate them. To generate inflation, as I mentioned, we require a sufficiently negative pressure. And you can achieve this whenever it's the case that the kinetic degrees of freedom is subdominant to the potential degrees of freedom, right? So when half phi dot squared is significantly less than v of phi, then according to those definitions earlier of the mass density and the pressure looks like minus v of phi, and that looks like minus rho. So I get a sufficiently negative pressure. And under such a condition, you could substitute this into the two equations up here, assuming k is equal to 0. You get a situation where h dot is roughly 0, right? So when I drop these two terms and I drop this, I end up, I'm assuming a flat scenario for the sake of argument, then I get these two equations, and these two equations imply that h dot is roughly 0. And so when I have a constant Hubble expansion rate, it is now a constant, the scale factor is exponential, and I end up with inflation. Okay, so this is how one can realize inflation. So in terms of time, I was wondering whether I should continue. Nick, would you like me to continue?
So, I mean, you've been talking for nearly an hour, so
okay.
If this is a natural break, it might be a good point to take some questions, but I mean, it also depends how far you need to get after as well.
Yeah, I'm about a third of the way through, but we can skip through some of the initial conditions problem stuff and move on to the multiverse cosmology stuff. So I'll find a natural way to do that, but we could break here, or I could go on for another 5 minutes or so maybe, and then we could break, if that sounds okay. Okay.
Yeah.
All right, let me go on. Yeah, let me go on.
Yeah, take another 5 minutes, and then we'll see if people have questions, but also people can sort of think about questions or type them up during the break, and we can sort of start off with those as well if necessary.
Okay.
But if there's a little more natural place to stop, then yeah.
Yeah. Okay. So I think I can find a place. All right. So this is the physics of inflation in the simplest possible model. And what we've done is we've introduced new degrees of freedom, right? So there's a way using this particular setup to solve the flatness problem, but we've introduced a scalar field, which you need to account for, and we've introduced a potential v of phi. And then there are conditions like these, which I said are required to give rise to inflation. And so you could ask various questions, such as, what are our expectations about the relative balance of these two terms in the very early universe? And then, even more importantly, the above conditions a special case, right? Remember I mentioned earlier on that in fact I've set phi to be homogeneous, so that I've ignored gradient degrees of freedom. Couldn't they somehow spoil this relation, right? And the answer to that question is yes, they could. The more general issue that we're getting at then is really this, namely, how special are these conditions that lead to inflation? And this question arises from one point of view, regardless of whether you think inflation solves the fine-tuning problems of the standard Big Bang model of cosmology. You could ask this question of the theory in isolation, right? Okay. So, let me ask the following question. Why do we worry about this problem in the first place? I mentioned some of the motivations for that earlier. Namely, one motivation is that, this fine-tuning is sometimes suspicious, and maybe this is a situation where we need to worry about it. Another way to think about this, and I think this is interesting because there's been a response to it, is the following, that we don't quite know. The idea is that inflation kicks in when the universe is described via a space-time which is, at least semi-classically viable. So it's described via Einstein's theory of general relativity, possibly quantum fluctuations. How those fluctuations become classical is another issue. And so we don't quite know what the physics is at even higher energy scales. And so the idea is that maybe it's a good thing to have a theory that is agnostic, as it were, as to what happens at the highest energy scales. So that higher energy theory, whatever it might be, has a larger space in which to land, as it were, a larger space of initial conditions in which to land. This is one way of thinking about why you would look for genericness. And this particular way of thinking about things does indeed focus on genericness. This lower energy account should be generic in the space of physically possible states, or even physically reasonable states that could arise in this unknown higher energy theory. You might not find this particular response particularly convincing. This is a quote from Penrose, who wrote a paper criticizing inflation, 1989. He says, "It seems to me that the idea of trying to obtain a universe in the form that we know it by applying time-symmetric physics to a generic, unconstrained initial state is basically misconceived," right? This is a notion that the project is somehow problematic. This focus on genericness is somehow problematic. Why don't we come up with a way of explaining how it, I don't know if this is an accurate way to paraphrase what he has to say. Let me add to it at the very, possibly, that the question one could ask is, why not why shouldn't we come up with a way to actually explain that initial state, even if it's very special? Why don't we focus on that rather than focus on something like genericness, focus on something like agnosticism to high energy completions? That's the sort of flip side, the motivation to set the kind of motivation that people use in the context of inflation aside, and to try for a different path. And Penrose has a conjecture which gets at something like this. It's speculative because it deals with quantum gravity, but nonetheless, it's a different way to address the motivation. Okay, and all right, so then there are a number of problems here that relate to the initial conditions problem. And let me point out two aspects of this, and then we can break. So the first question is, to what epoch does initial in fact refer? And so here is a timeline of the very early universe. It's a cartoon, obviously. There's a singularity, there's a Planck era where quantum gravity effects kick in. 10 to the minus 43 seconds is the Planck time. Things become describable via general relativity, somewhere around here. Inflation, maybe it begins here, maybe it begins here. We don't know. If it's the case that inflation begins immediately after the universe emerges from the Planck era, then the initial part of initial conditions refers to the Planck time. If inflation begins here, then initial refers to either this moment, namely when the universe first emerged from the Planck era, or it refers to when in fact inflation indeed began, right? And this is the kind of thing that I was thinking about focusing on, but may not, because I want to get to the multiverse problem. In any case, there is an issue here about what it is, what means by initial. And as I mentioned earlier, there's also this problem of which conditions you might worry about. Initial conditions describing the universe are the same everywhere in space, namely it's homogeneous, and the same in all directions, namely it's isotropic. This is one class of conditions. This is a simpler class of conditions, arguably, than the class of conditions which includes spatially inhomogeneous initial conditions and anisotropic initial conditions. There's been a bit of work done on both of these. There's more numerical work coming out looking at the second issue. It's a larger challenge, but I think it's live. But I think this problem is live. So all right. So maybe what I'll do is I'll stop here. And we can take a break, and then I can come back and pick up from roughly where we left off.
Yeah, and I just was thinking about the double pendulum case, and in general, like what exactly is problematic for fine-tuning in the context, say, of the standard Big Bang theory, and why is that different from, say, a double pendulum if you're trying to explain that with classical mechanics or chaos theory. Mm-hmm. And I was thinking one of the differences here is that, like, it depends what exactly you are explaining. So one thing is to say why exactly, say, the pendulum right now is at this very specific configuration. And like, in a way, like you would expect that, because the theory is deterministic, you would expect, yeah, that could only have happened if the initial configuration was this one. Mm-hmm. And then, you know, Newtonian mechanics, and you know, the normal laws or the forces in place. And so you get a causal link between the initial state and the final state. Mm-hmm. So there is no mystery there. Like, of course, you have to pinpoint to a particular unique configuration initially to get a later one, right? But on the other hand, and in a way, like that's what I think you would expect to in cosmology. Like if you ask why we have this very exact current configuration, say, of matter, then, I mean, there is a way in which you expect there is an explanation that is causal, right? It goes back to a very particular initial state, and you can like follow, say, the chain of events until we reach this point. So in a way, that's the same thing. Like there is no mystery there, but the question is, like, I think one of the pendulums all upside down. Like imagine they're in the unstable configuration. So it's not a double pendulum, just a normal pendulum, but like on the very unstable configuration. And I say I see 10 of those, and then I go to another building, and then I see again like all the pendulums are like upside down. That's weird. Like that seems to require an explanation. And one explanation is, well, there was this person, this crazy person that was playing with all the pendulums and tried to make them upside down, right, or something like that. So, so chaos theory or classical mechanics wouldn't explain this. Like they would explain why each pendulum reached that position, of course, but you need like an extra thing, like this person likes pendulums that are upside down or something like that to account for the weird situation you are looking at. So I wonder if this helps in some way to like approach the question of why fine-tuning is problematic. And I think part of the thing is depends on what you are trying to explain, like where you're explaining a very specific thing or a more generic thing, like in many pendulums upside down or something like that. Yeah, so I wanted to
That's
hear
interesting. Yeah, that's interesting. So I guess let me ask the following question. Is one way to phrase what you're asking that you're worried about what one means by salient, actually? What are the things that are actually important in terms of requiring an explanation, right? And I totally agree with you in the case of, and I guess what I'm saying is that I would agree that it seems that there is something important about the 10 pendula, all individual pendula all standing up straight, and that maybe but so I don't have a crisp way to distinguish or to tell you why that's important in the same way that flatness is important. But there is a sense in which I've made a connection between what is salient. I've at least identified something that's salient in both of those cases, which isn't just a trivial case, which is, exactly as you point out, that of course the double pendulum's going to execute a particular kind of motion because the initial conditions were set to be just so. But somehow that's the wrong question to ask, right? In making sense of what is problematic about fine-tuning in the context of classical mechanics. So that's one thought. I don't know if you agree with that, whether it's sort of the notion of what's really playing important role here, which we haven't actually made sense of and haven't defined crisply, is this notion of salient phenomena.
Yeah, I agree. I think, intuitively what's salient is what's making the difference here. So I agree with you in that. Yeah.
Right. I mean, maybe one way to cash this out is in the case of a coin flips, is that the probability of fair coin, the probability of getting tails, 1,000 tails in a row, is the same as the probability of getting any other configuration. But somehow 1,000 tails in a row requires an explanation of some kind, right? That actually goes beyond just the raw probabilities here.
Yeah, and I think, as you said, it has to do with like the class, like you have to go beyond the very particular event you're looking at, like similar macro events, if you want, like.
Right. There's a coarse graining. There's a coarse graining phenomena that happens that is ill-defined, but which I think physicists are sometimes very good at figuring out, even though it's ill-defined. But there isn't a prescription, right? So you can go wrong, right?
Yeah. Thanks. That's helpful. I think, I agree with that.
Okay.
So Jeremy has a question too in the chat. Do you want to have a go at that now? Or, I mean, or you can save it to the end if you want to go on. But it does seem to apply to the initial conditions you were just talking about.
So let me, so Jeremy's asking, do we need genericness to motivate a choice of initial conditions? For example, might we use simplicity and or links to a theory of quantum gravity? Do you think such considerations ought to complement genericness. Great. So, so sorry, and maybe this goes back to the second half of your first question, Jeremy, that there are other theoretical virtues in play here that might, that overlap with, that may take precedence over the notion of fine tuning, such as exactly what you point out, this notion of simplicity versus complexity, and any other, any other set of theoretical virtues that you might wish to point to. So, so from that point of view, there are likely other ways to think about this. There are likely other motivations for something like worrying about the initial conditions problem. The one that's the sort of most somehow immediately presents itself is this notion of genericness. But it would be interesting to hear more about, the interplay between something like the initial conditions problem and some of these other theoretical virtues. So if you have something in mind, feel free to throw that out there. Yeah, I mean, it's interesting. Yeah. Yeah. Okay. So it's not quite an answer, but it's an I agree with you that there are.
Could I follow up on that briefly?
Yeah.
Or do we want to just get moving? Yeah. So what I don't necessarily have great ideas. I was more interested in the possibility of if you were to fall on the more skeptical side of fine tuning that you were suggesting in the earlier reading, if the associated motivations that you were drawing for solving problems like the initial conditions problem could just be separated from the genericness considerations. Yeah.
Sorry, say it again. So you're worried, what is it you're worried about? That
I was just wondering the extent to which the way that you were discussing the initial condition problem just now, the way that the extent to which you feel we might just take this account and separate it from genericness if we fall into that skeptical reading of fine tuning that you were discussing before.
Yeah, it's interesting. I mean, I'd have to think about it. I don't have a quick response for you. That isn't that it's somehow very important. That somehow, you're right. So what I'm sort of arguing is the initial response that I have, that in fact it's tied up in that with genericness in an intimate way. But I'd be curious to probe the separation that you have in mind. But I'd have to think about it a little bit more. Yeah. Okay. So maybe what I can do is continue and give you what I've decided to do is I was going to present some work that is related to what I've been working on, but I'm going to skip that, and I'm just going to give you a flavor of how people worry about the initial conditions problem for inflation in some simple settings to really hammer home, as it were, how it works, and then we'll move on to the multiverse problem. So here is so as I mentioned, there's two classes of conditions here. There are initial conditions that describe a universe that is homogeneous and isotropic, and then there's not homogeneous and isotropic. And here is a situation where I'm going to look at a case where we're worrying about homogeneity and isotropy and asking, what does the initial condition problem actually look like? What does the physics look like? So this is a potential. It's a particularly simple potential. It's n squared 5 squared. What you'll notice is that, so here's the first Friedman equation. What you'll notice is that if I set k to be 0, then if I take the square root of h, I can put it straight into the continuity equation, and I get an equation that stands on its own just for phi, right? So somehow, by virtue of this very special condition where k is equal to 0, I end up with a situation where those two functions that I need to solve for, namely phi and a, I can solve these two equations independently, as it were. I can first solve the phi equation, and once I've solved the phi equation, I can put it back into this, and I can solve for a. This then describes the dynamics, as it were. It's a second order differential equation. You can solve it numerically, and the initial conditions that you have in mind are then the initial value of the scalar field and the derivative. the velocity, as it were, of the scalar field. If you, in fact, so if you solve you solve that differential equation with different initial conditions in this two-dimensional plane, you get the following picture. So imagine, say, you start, imagine you start here. So this is a case where phi is positive and phi dot is negative. So I'm starting like in this picture here where phi is positive and phi dot is negative, namely the field is moving towards 0. What actually happens is that very quickly, so the field itself moves from here to here. Sorry, moves from somewhere like here to here, but the velocity drops very quickly. So there's this very large frictional effect, as it were, and the trajectory starts to follow this attractor, which is in fact an inflationary attractor. And then as I follow this through 0, what's now happened is that this ball, which is representing the value of phi across space, starts to oscillate oscillate around 0 and asymptotically comes to rest. So all the quadrants you can get by symmetry. So this quadrant essentially tells you everything about what's going on. And you can ask the question, well, imagine I have a surface of, you could ask, so very simply, you could ask what fraction of this space leads to inflation, right? Leads to enough inflation to solve something like the flatness problem, or the flatness problem, or the horizon problem, this uniformity problem that exists, which I mentioned really early on. And to actually make sense of that, you probably notice there's a problem here immediately. To make sense of it, you need to come up with a measure on this space, right? You have to come up with a sense of how much of the space is in fact driving you into these inflationary attractors, driving you into sufficient amounts of inflation. So there's an interesting paper that you might be interested in looking at by Grant Remen and Sean Carroll on this in 2013-14, where they work on this particular problem. They come up with an effective measure on phase space. Okay, and so here's the state of play on the initial conditions problem. The state of play is the following. So work so far, with one exception that I'm aware of, and I'd be very happy to hear if you know of other exceptions. Work so far has studied this initial conditions problem by looking at a single inflaton potential at a time. So people who are working on this, doing lovely work on this, and some of this is quoted down here, will set down a particular potential, which is representative of a class of potentials that will, and then study, try and get a sense of how probable inflation might be. And there are general points of agreement. Things are starting to look a little more comprehensive in this context, but I don't think they're quite comprehensive. And the one point of agreement is that large field models of inflation tend to be more robust than small field models of inflation. And the distinction between large and small here refers to the excursion of the scalar field on the potential. So along the potential, if that excursion is more than a Planck mass, that's known as large field inflation. So m squared, phi squared, the example that I gave is an example of large field inflation. We could imagine that there are models where the potential is balanced in such a way that inflation only occurs for a relatively small excursion of the scalar field along the potential. Those are known as small field models. Those are less robust. That might not be super surprising to you. Large field models seem to have more room when things could go wrong, and so it might be a little more stable, as it were, or robust. And that certainly happens to be the case. The one exception that I'm aware of it because I worked on it. So if you're interested in that exception, you can read about it. This is work done with David Kaiser. There's a physics paper on this. That's the first one, and then a philosophy follow-up paper that tries to grapple with some of the conceptual concerns that arise, you can find here if you're interested in it. So so what I might do is, that is everything that was half of what I was actually going to say about the initial condition problem. I'm now going to skip ahead to the multiverse problem and make sure that we have time to go through that. If we have time and people are interested, I could tell you more about this work, which is what I was going to say a little bit more about. originally. So let me skip ahead to the multiverse problem. Okay. So as I mentioned, you might ask the question, does inflation describe only the structure that we see? And as I say infamously, the answer to that question is no. If inflation occurred at energy scales that are higher than those involved in the imprinting of these density differences in the very early universe, then it's the case that, and this is a fairly generic claim, that inflation is eternal. Inflation is future eternal. And so the contention then, the claim is that generic kinds of potentials that I showed you earlier, including m squared phi squared, those kinds of potentials give rise to a vast causally disconnected set of domains in which parameters can vary depending on the particular model from one domain to the next. And there is no, it turns out there's no agreed, as I mentioned, there's no agreed upon theory or model that gives rise to a multiverse, but as I said, the physics is speculative, but there are hints that structures like this might exist. You have to do something like semi-classical quantum gravity to get this kind of effect. And I'll give you a couple of examples of how this works. Some of the ways in which inflation gives rise to a multiverse are a little more mathematically tractable, a little are on sounder footing than others. What I'll do is I'll point to the two main ways in which people talk about how it is that you generate a multiverse from inflation. So the two mechanisms are false vacuum eternal inflation and slow roll eternal inflation. Here is an example of false vacuum eternal inflation. Here I have the, so again, imagine a homogeneous situation. I have the inflaton, it's trapped in a local minimum, a false vacuum as it's known. Then what can happen is that it can quantum mechanically tunnel along this line into this part of the potential, or it can sort of rise through thermal fluctuations and then roll down the potential in the same way that you saw in the case of m squared phi squared, and give rise to a universe with potentially, depending on the slope of this potential and the shape of the potential, give rise to density differences in the early universe. So this kind of transition. So imagine. So here's how you think about this. Imagine you have a space, a three-dimensional space, and you have the potential. You have the whole space is uniform. There's a value of the scalar field phi is uniform. And then this transition occurs. This transition creates a little bubble, and the bubble expands. The background is expanding because the background is inflating. Notice that if this is just sitting there, then the kinetic energy of this particular field is zero. And so this is potential dominated, so it's going to inflate. So I have a background which is inflating, and then I get these little bubbles which form. The bubbles then inflate, and this continues to happen in this sort of stochastic way, which is determined by by quantum fluctuations, eventually giving rise to this massive structure where I have pocket universes all over the place. And if this rate of tunneling here is significantly less than the expansion rate, then, as one example, then inflation never ends, and the background spacetime, as I said, becomes populated, in fact, with an unbounded number of domains, with an infinite number of domains. So this is one way in which you can get eternal inflation. You may wonder where this potential comes from, right? And you would not be alone in wondering where that potential comes from. Okay, so here is another way in which you can generate eternal inflation. As I mentioned before, the simplest examples of, so here's m squared phi squared again. The scalar field will roll down the potential, but sitting atop of this this evolution are quantum fluctuations in the value of the field, and if these fluctuations are large enough, they can counteract the roll of the scalar field down the potential, and they could cede, as it were, regions which continue to inflate. So, and in fact, you can rig things in such a way that this will lead to regions that are continuously inflating, as in other regions inflation stops. So this is less, I think it's safe to say that this particular mechanism, well, let me not make the comparative claim. This is another way in which you can get a multiverse. It's not clear how generic eternal inflation might be, but it really is a prediction of a wide class of inflationary models. So this really is one of the simpler models, and you get eternal inflation. Sorry, this is supposed to be m squared phi squared. And you get eternal inflation in this kind of setting. And the multiverse problem is not the problem of where the potential comes from that I mentioned earlier, which is a problem. It's not the problem of how you describe the multiverse theoretically, but the problem that I have in mind and the problem that I want to focus on is how do you confirm such a theory? How do you confirm a theory of the multiverse, particularly in light of novel features of our observational situation in the multiverse? So I'll talk about this in a moment. I want to come up with a philosophical scheme which tries to get at theory confirmation. Okay.
Can I ask a quick?
Yeah.
I think it's a quick question. It may be a long answer. What is a quantum fluctuation? I mean, are you thinking of this in terms of something like a quantum jump, so that it's a multiverse of sort of, I mean, there's a single kind of classical multiverse of different universes, or are you thinking of it along the lines of sort of kind of many worlds, and so these are in different kind of many world branches?
Yeah, great. So you're dead right. There is a long answer to this question. Let me give you the simplest. We could talk about some discussion about how you could get a multiverse in an Everettian context. There is a story that you can tell that gives you one. Let me just make the caveat. One caveat is that the typical Everettian scenario, which you may have also heard of as giving rise to a multiverse, namely where you're thinking about Everettian branching occurring on tabletop type experiments, isn't quite the multiverse that I have in mind, but there is a story that you can tell that is Everett based, that gives rise to a multiverse where these different branches have different values of the constants. How I'm thinking about quantum fluctuations in this context is really that they're seeding, and in particular, I think in this context, they're seeding, there's one classical space-time, semi-classical space-time, and they're seeding bubbles that are existing in that one sort of classical space. There is another problem with how it is that you get quantum fluctuations to become classical. This is the usual problem, and it exists in cosmology as well. So, so that original paper that I mentioned, which goes into a variety of different problems, is one of the problems that they highlight, the quantum measurement problem at some level. But yes, imagine a one large space-time with bubbles in it. Okay. And not an Everettian situation, to make things the most simple. Okay, so here is here is the assumption. Assume that arises from these considerations. Assume the multiverse consists of many domains, each of whose inhabitants, if there are any inhabitants, cannot observe or otherwise interact with any of the other domains, and assume that the parameters that enter into our effective laws of physics vary from domain to domain in principle. Okay, there's a lot you have to do here to get this to work, but you can do it. Regarding confirmation, the simplest thing to try is to simply say, well, I look out, I a third person, well, sorry, so I should be careful. Let me just say, I notice that I have a connected space-time, with disconnected pieces, as it were, where parameters vary. Maybe there's a probability distribution that I can set down, that I can extract from the theory, and I can compare that probability distribution with our observations, right? So in our domain, we go out and we measure this vector of parameters, lambda, and we get this value in this schematic plot. And then we look out at the multiverse or our theory of the multiverse, and we notice that we can extract this probability distribution. Why don't you just compare the peak, namely this value with this value, right? So the simplest kind of statistical test. maybe you can make that work in a multiverse context, and then confirmation just becomes the usual kind of notion of confirmation, statistical confirmation, where we want our value to lie under the peak of this curve. Okay. All right, so it's easy to state, and it's very difficult to make this comparison make sense. So there are 3 sub-problems that arise in trying to make this comparison, and let me go through them one by one. As I said at the outset, I think all 3 of these problems are open. Some are more contentious than others, and I think they're kind of exciting and interesting. Okay, so the measure problem is the following. It's the first problem that you run into. And the question is, what are the elements of the sample space? So I have in mind, I want to write down some sort of probability distribution over parameters. And let's say, here's my multiverse, right? So here's a toy multiverse, not to scale. I have I have one domain here, one domain here, and I have one domain here. The values of this vector of parameters takes the same value here and here. It happens to be our observed value. And here it takes this particular value. The question is, what is the probability of our observed value? Is it 2/3 because 2 of the domains have instantiate that value and 1 does not? Or is it the case, I mean, you may want to consider this, if I do this by volume, right, then this volume here seems to be much larger than these 2 volumes here. And this volume may be 10 to the 10 times larger than these 2 volumes here. If I choose volume as the sort of defining feature of the problem, then the probabilities will change significantly. So there is some sort of choice that you need to make. And that is one aspect of the measure problem. And then it happens to be the case that natural measures, as I say here, over reasonable candidates for elements of the sample space, like let's choose domains as the simplest thing, those kinds of, if we can define domains in a crisp way, which, you know, they're according to something like false vacuum maternal inflation, you might be able to, natural measures are then face problems of regularization. If you ask the question, what's the probability of some property S, and you define that probability to be the measure of the regions of the domains where that property S obtains divided by the measure of the whole space, you typically get something like infinity over infinity, right? And so you have to regularize in some way, and the answer, the final probability that you get depends on the regularization. Alan Guth describes this very clearly, I think, in a way that really does shed light on this issue. Imagine asking the question, what's the probability of randomly picking a natural number and getting an even number? It's the same kind of problem. The total number of even numbers is infinite. The total number of natural numbers is infinite. The answer sounds like it should be a half, but the answer actually depends on how it is that you perform, how it is that you compute the probability. If you just take the first n numbers, ask how many of them are even. Did I say even or odd? Let's say I said even. If I take the first n numbers and I ask how many of them are even divided by the total number of numbers, I'll get roughly a half, depending on, I get exactly a half or roughly a half. And if I take the limit as n goes to infinity, I end up with a half exactly. But I could order them in various different ways, right? I could order them such that I've picked the first number, I pick 2 odd numbers and then an even number, and 2 odd numbers and then an even number, and so on. And that particular ordering, that regularization scheme, will give me a completely different answer, right? It won't be a half. So this is a problem that you run into. And there is no sort of, you know, the people have tried to make sense of this. There is no agreed upon solution to the measure problem. Okay, so even if we solve these problems, we run into the second subproblem. And the second subproblem is the following, that it's expected that for any reasonable theory of the multiverse and any reasonable solution to the measure problem, any solution to the measure problem, the probabilities for our observations are going to be small, right? There is something special about all this in a multiverse context, namely that much of the multiverse isn't going to look like our domain. So then the instinct might be to say, okay, say I'm lucky enough to compute something like this probability distribution. It's generically the case that our observed values of this vector of parameters is going to be highly unlikely. So that might be enough to then set aside, you could get off the multiverse train, as it were. You might wish to say at that point that, well, this just confirms all theories of the multiverse. And there's another way forward. So that's not necessarily something that you have to do. I think some people do that. Some people do, as it were, get off the multiverse train. I don't think it's something you have to do. What you can do is you can conditionalize the distribution. It's like asking a different question of the theory. You're asking the following question, namely, why don't I ask the theory what it is that I'm going to see? That's one way to phrase it. So let me restrict attention to just the domains in the universe where we could exist, right? So the idea, the rough way to think about this is I look out across the multiverse, and I'm now going to excise parts of the sample space, get rid of the domains where it's not possible that I could possibly exist, renormalize the distribution, and then make the comparison, right? So I set down some set of conditions C, I compute the probability of the vector lambda given the theory and the conditions, and then I make the comparison, right? Okay, so you might imagine there are all sorts of problems that arise. So there is really a spectrum of conditionalization that you could enter into, and it's a bit of a mess. What's a spectrum? You can read about it in this paper by Anthony Aguirre and Max Tegmark. You could do one of three classes of things. One class of things is you could do nothing, right? You could just simply not condition at all. And this is known as the bottom-up approach. Another class of things that you could do is known as the anthropic approach. So you select observables in our models that we believe are somehow relevant to our existence, right? And then you just look at those domains in the multiverse where those observables take those values and then do the comparison between our observed values and what the probability distribution tells us. That's another approach. The problem with this approach sort of is immediate, namely, how do you characterize our observational situation? And which values of which observable should we conditionalize on? So really, there's this issue of what it is that we mean by us at some level. And okay, so this is the problem with anthropic conditionalization. The other thing that you can try and do is you can say, well, let me just take everything that I know, right? Why not? Why forget about sort of an anthropic approach? Let me just take all my data and fix all the parameters, except for the parameter observable that we want to measure, and then recompute the probability distribution and compare the probability distribution with the observed value of that particular thing that we haven't conditionalized on. So what data do you choose? This is the problem, right? As you know a lot, you know a lot, and you could fit, how do you manage the data that you have in such a way as to do this? I mean, you may have instincts as I'm giving these to you. I'm trying to make it sound worse than it is. Sorry, no, I think I'm making it sound worse than it is. There are ways forward in some of these cases, and you may have instincts about how this works. I'd be curious to hear about them. But this is the sort of worst case scenario. Okay, so how do we do anthropic conditionalization? Let me point out one principle that people talk about, just because you may have heard about it, and you will hear about it if you think about these things more. Brandon Carter in 1974 formulated the weak anthropic principle, and this is, and I quote, "What we can expect to observe must be restricted by the conditions necessary for our presence as observers," right? This is saying you're not going to see what you could not possibly see. And so from one point of view, it seems like, it's sound. I don't know how much work it's going to do. How do we understand this? Could we use this kind of principle to implement the anthropic approach that I was talking about in the last slide? So generally, I think the weak anthropic principle, which is what WAP stands for, says, beware of selection effects. right? So notice that our situation is somewhat privileged, and we can only exist in places where parameters take certain values. For example, the cosmological constant's a good example. If the cosmological constant is too large, it'll blow everything apart, and it won't be enough time for things to form. And there's a sort of dual problem when it's too negative. So the cosmological constant has to sit in a certain zone, a sort of anthropic zone, as it were. And notice that that is going to be something you're going to find. And keep that in mind when you're engaging in theory confirmation. Is the one way to understand beware selection effects. So notice that if you do try and invoke the weak anthropic principle, or you do try and implement it in your conditionalization scheme, it's playing a role in some way. It's not just saying beware selection effects. You're now using it to pick out theories, right, in some fundamental way. Or you're using it to compare two theories when it's the case that you have two theories to compare and you want to compare them. So there is work that it's doing, and this may strike you as problematic. I don't know. So let me put this whole issue in a different way, and this is roughly true of the top-down approach as well. A specification of these kinds of conditions that go into the weak anthropic principle, in effect, select a reference class, right? So there is a reference class problem which underlies the conditionalization problem. The conditionalization problem is, in some sense, a reference class problem. Okay, so here's another issue for either anthropic or top-down conditionalization. It's natural to require that the observable that is being predicted, right, the thing that you're trying to predict, is correlated with the conditionalization scheme, right? Otherwise, the conditionalization makes no difference. But somehow it's not perfectly correlated with the conditionalization scheme. So it's not the case that your conditionalization scheme somehow fixes that value, right? There'll be something circular in that. And that might strike you as problematic, or not. This may strike you as unfair. So I'd be curious to hear more about that. So at the very least, in the worst case scenario, when it's not clear how the observables are correlated with the defining features of the conditionalization scheme, it's not clear how the thing you're trying to predict is correlated with the scheme. And sometimes it's not in eternal inflation. The need to strike a balance between these requirements is tricky, right? So in short, the conditionalization problem is the following. How can we distinguish the observable to be predicted? So this part of the conditionalization problem, sorry, is how can we distinguish the observable to be predicted from the defining features of the conditionalization scheme? All right. So you've solved the measure problem, you've solved the conditionalization problem. You've done very well. You haven't done enough. There is one other problem, and the problem is the following. It's known as the typicality problem, that for any appropriately conditionalized probability distribution, how typical, the question is, how typical should we expect our observational situation to be amongst the domains or regions to which this distribution is now restricted? We've restricted our attention to certain domains, so we've somehow fixed the measure. We know what the conditions are. We look out, and there are a bunch of domains we could possibly exist in. And there's a question of now how typical we are. This is only a live question if it's really the case that in all these domains that we've now restricted attention to, there is something different about them, right? That, for example, the next experiment that each one of these particular domains, say that each one of these domains is a civilization, it looks roughly like us, and they're going to go out and make a measurement, they're going to perform an experiment. If it's the case that, and that there's at least one, okay, I don't want to put this too precisely, if it's just the case that you can get variation in the outcome of this experiment, then the typicality problem is a live problem, right? And there are two, and I'll say this again in a second. there are two distinct camps about typicality. There is for typicality, and then there is not necessarily for typicality, right? So namely, typicality is just an assumption. So for typicality has been argued by Garriga and Vilenkin in these two papers. Sorry, this is not very much information. I can certainly send it to you if you're interested. And for typicality says that we should reason as though we're typical members of a suitable reference class. So you've solved the reference class problem in the conditionalization as part of the your solution to the conditionalization problem. And the argument here is that we should assume that we're typical. The other option is that we should allow for a range of possible assumptions about how typical are. We may be typical, we may be atypical. And somehow a conformational scheme should take this possibility into account. Okay. So so let me elaborate on both of these points of view. I'm going to try and stay agnostic, and would you be interested to hear your thoughts on where you stand. So here's a quote from Garriga and Vilenkin, and this is the point of view that argues for typicality. I'll read it because I think it's instructive. It tells you how people are thinking about the multiverse problem generally. So they say probabilities in the multiverse can be calculated by assuming that we are typical representatives in a given reference class. But is this class well defined? This is sort of like the conditionalization problem. What should be included in the ensemble in which we are supposed to be typical? There is a widespread belief that this question is inherently vague, right? A belief which I'm trying to transmit, and that there are various possible choices for the types of reference objects that should be, which should be counted in. Here we argue that the ideal reference class for the purposes of making predictions can be defined unambiguously in a rather precise way as the set of all observers with identical information content. So here is that reference class, identical, everybody with identical information content. And so say you can't do this, even if it's the case that you can't identify all the observers with identical information content, you're somehow limited because that is too tricky. Once we have gathered all practically available evidence, the optimal strategy, so there's a notion of optimality here, for making predictions is to consider ourselves typical in any reference class we belong to. Unless we have evidence to the contrary, in the latter case, the class must be correspondingly narrowed, right? So they're arguing that they do identify a reference class, namely they provide a solution, as it were, to the conditionalization problem, namely those with identical information content to us, and they assert that we should assume typicality with respect to that class. And even if implementing this identification is problematic, we should assert it anyway, right? Okay. So then a question arises, why is this strategy optimal? And the answer they provide is that it simply improves the odds of being right. And there's a story they tell about this. We can come back to that. But this is the kind of argument that is made for typicality. Here is the argument that's made for the idea that typicality is just an assumption. So this is by Mark Schrodicki and Jim Hartle, 2010, paper called Science in a Very Large Universe. They say, and I'll read it again because it touches upon some of the themes that we've been discussing or that I've been telling you about. If the universe is very large in space and or time, so they have in mind a multiverse. I don't think they use the word multiverse in the entire paper. The probability becomes significant that the data on which we base predictions is replicated at other locations in space-time. Okay, so exactly our data comes up lots of different places. The physical conditions at these locations that are not specified by the data may differ. So there are other things that are different that the data does not specify. And they say predictions of our future observations therefore require an assumed probability distribution, which they call the zero-graphic distribution. I think for Xerox, because Xeroxing something is copying it, and there are replications of our data in various places. Predictions of our future observations require an assumed probability distribution for our location among the possible ones. And then they say it is then the combination of the basic theory plus the zero-graphic distribution that can be predictive and testable by further observations. So here they narrow their focus on a reference class that consists of replications. So this is something like top-down conditionalization, maybe. But in the context of this reference class, their zero-graphic distribution allows for different assumptions about typicality. So it allows for varying degrees of atypicality. And as I said, you test what they call frameworks, the conjunction of theory plus typicality assumption. In fact, embedded in their typicality assumption is something like a conditionalization scheme. So what you're eventually doing is testing the conjunction, according to this way of thinking, of theory and conditionalization scheme and typicality assumption. Okay, so here's the thing that I wanted to come back to give you a sense of what the problem is and whether it's in fact so the nature of the problem. So one way to understand a version of the issue is the following. Imagine, so here are my domains. So to answer Nick's earlier question, this is how I'm thinking of the multiverse. I have like a bunch of domains that are sitting in front of me. They are subjectively indistinguishable space-time regions in a multiverse. And at each one of these locations, let's say there are observers, and they're about to perform an experiment. They're going to make a future measurement and of the color of a square, let's say, and 10 to the 10 of them are going to see an orange square and 2 of them are going to see a blue square. This is the setup. So most of these regions will measure orange, where just 2 will measure blue. So the typical such region will measure orange, whereas the atypical region will measure blue. And in this particular case, which is a case that arises in models of eternal inflation, our assumption of whether we are typical or not makes a difference to the predictions, right? If we assume we're typical, let's say you don't, I can't cover the screen, but let's say you don't see anything down here. If you assume you're typical, you would expect to see orange, right? If your theory tells you this, you expect to see orange, whereas you would not expect to see blue. So it then makes a difference to whether the theory is confirmed or disconfirmed, whether it is that whether you assume you're typical or not. This is the kind of issue at play. So that is what I wanted to say about the multiverse problem. It is a conjunction, as I say, of 3 problems: the measure problem, which is a technical issue with some conceptual input; the conditionalization problem, which if you simply try, well, I think that the sort of technical and conceptual aspects of this problem come together, and the typicality problem, which seems very conceptual at heart. But there's also a question how you implement something like typicality via probability distribution, via xerographic distribution, if in fact you're open to the idea that you can argue that typicality is just an assumption. So there's a question of how you implement that technically. Okay, and the final thing that I wanted to say is the following, that I've presented 2 problems, and the 2 problems are slightly different in nature, I think, as I mentioned at the outset. Regarding the initial conditions problem, I think that there is, we don't need to wait for a more complete understanding of the very early universe in order to evaluate whether inflation is finely tuned. The examples that I gave, the example that I pointed out in the case of a homogeneous space where I had m squared, phi squared, these are the kinds of ideas of people probing theoretically, and then there's numerical work that's looking at situations which are more complicated than that. And I think there are model-independent ways of doing this using effective field theories, things that I've worked on that we can talk about if people are interested. So we can now credibly aim to evaluate, this is the claim, whether inflation is susceptible to the same general problem it claims to solve, namely a fine-tuning problem with the standard Big Bang model of cosmology of the 1970s. But you can ask this question regardless, as I said, of where you stand on whether the standard Big Bang model of cosmology is finely tuned, or whether it's finely tuned or not. And then with regards to, so this is sort of a current problem, I think it's live. And then there are aspects of the assessment of the multiverse problem which really do require a more complete theory of the very early universe, so where you get the potentials from, precisely what the variability looks like. But I think each of these sub-problems you could plausibly look to try and make sense of them, even in a broader philosophical context. Okay, so with that, I'll stop there, and I'm happy to take questions. I do have a bunch of other stuff I could talk about if you wish to hear more about the initial conditions problem. But okay, thank you.
Thank you. Yeah. So yeah, lots and lots there. Okay. So I have a call for questions. You can put them in the chat. You can raise your hand in the participants. But I see a question from Josh Hunt. I can also read chat questions.
Oh yeah,
too, but
that's fine. Yeah, thanks so much for the talk, Feraz. That was fascinating.
Thanks.
My question is, so with respect to the conditionalization problem, if you were going to be comfortable with something like a weak anthropic principle, and if it turned out that all of the parameters that we might have thought were finely tuned were actually necessary for life as we know it, would that solve the initial condition problem using the conditionalization problem?
Sorry, so how are you proposing to solve? You're saying, I don't see the...
It's like, yeah, so if it turned out that all of the parameters that we were worried about being finely tuned, their particular seemingly finely tuned values were actually necessary for life as we know it, and then you plug that into the conditionalization problem, would that eliminate the initial condition problem? Would it just eliminate the worry about fine tuning?
I don't know. I don't think so. So I think that, so let's separate two things. So one's the initial conditions problem for inflation, regardless of whether there's a multiverse or not. And the second thing is that there is this problem of conditionalization, which arises in the context of the multiverse. If it's the case that you're wondering about something like an analogous initial conditions problem that arises for parameters that enter into a multiverse setting, I presume. If it's the case that you find that the parameters that we think are finely tuned have to be set to be exactly so and are necessary for our existence, which does seem to be the case, you have a problem with fine tuning. You could argue that you need something stronger. I think you need something stronger. You need something like they must be this way, right? You need an argument that states that those parameters must be this way beyond the necessity for our existence to avoid a charge of fine tuning in that context.
Okay, yeah, I guess I'll follow up with you later. I feel like I'm still hung up on something. Thanks though.
Okay. What solutions to the multiverse problems best account for the infinite zero-point energy predicted by quantum field theory? So, right, so there are multiverse type solutions to the cosmological constant problem, which I think is what your question is getting at and above. But tell me if that's not the sense of your question. And sorry, I lost the question. Hold on 1 second. So, okay. So, yeah, you know, if you're asking the question, what kinds of multiverse settings are able to account for something like a small cosmological constant, it's, you know, the one that I could point to that I have questions about more generally are landscape scenarios in string theory, where you might expect to get significant amounts of variability, enough so that there's some probability that you might see a value for the cosmological constant that is that accords with what we in fact observe. But you know, there is no solution, as it were, to the multiverse problem. There's no actual multiverse. There's no agreed upon physics of the multiverse, as it were, and there are no individual solutions to the problems in such a way that I could that I feel comfortable saying that there is a solution to the multiverse problem that best accounts for something like the cosmological constant problem. So there's a way to account for our, so let me put it this way, there is a way to account for the value, the observed value of the cosmological constant in speculative multiverse settings, but you have to buy a lot of stuff if you're going to believe that solution. Buy a lot of stuff that's not well defined as well. So.
Yeah, so I actually have a question. So this entire presentation has been really helpful in as an introduction and going through the issues. Yeah, so my question has to do with the kind of, so I'm not sure whether I'm understanding this right, but the Friedman, is it the Friedman equation that you showed previously?
Yeah.
Would that be particularly for cosmic inflation as a general theory, or would it be the kind of multiverse generating sorts of cosmic inflation? Yeah. Or am I misunderstanding it in such that if you have cosmic inflation, you definitely would get a multiverse?
So if you have, so cosmic inflation requires, let's see, so cosmic inflation, as in the way that I've described it, includes this potential term. And for, it's hard to make this particular claim precise, but this claim is made that for most of these kinds of potentials, you end up getting a multiverse. You end up getting a multiverse, yeah. So the way in which that arises is not captured by the Friedman equation on its own, because this is just describing the classical evolution of the scalar field down the potential. But you need to add to this some quantum mechanics to get the multiverse. So it's a little more complicated. And in fact, even to account for the density differences, the energy the differences in energy density from place to place, you need to add quantum mechanics to the story as well. So this particular equation is just providing you with a way to get accelerated expansion or exponential expansion. Now, the issue about the precision, when I say that most potentials give rise to eternal inflation, you know, most needs to be, you could ask, well, what do you mean by most? You know, I mean, if I take a pen and I just draw a squiggle, right? That is a potential, it's potentially an inflaton potential, but nothing exciting is gonna happen with that potential. By exciting, I mean nothing inflationary is gonna happen with that potential. So that's the kind of, you know, question you could wonder about. Sorry, does that address your question?
Oh yeah, definitely. I'm not sure whether I can keep going, but I think, so if I'm understanding this correctly, it seems that this equation sort of like gives us a sensing on how we get inflation, and from cosmic inflation, we can explain certain things like the flatness problem and stuff like that. And we will need like a certain sort of potential, and it seems that in general, the sort of potentials that we get do give us eternal inflation that gives us the multiverse, but we also need like a little bit of like quantum stuff to like feed into it to get that kind of ontology.
Yes.
So if I'm understanding this correctly, would it mean that if we do in fact successfully do away with the initial conditions problem and so on and so forth, we I don't know how to say this, we would actually kind of resolve the fine-tuning for this particular Friedman equation, but we still need a little bit more to like push on forward to say the multiverse in general. Does that make sense?
So you're worried that there is another
necessary but not sufficient
to solve the initial conditions problem, right?
Yeah.
So you're worried that there's another initial conditions problem sitting in the wings, even if you solve the problem in the context of standard inflation, that there's a problem for, and there's a problem of initial conditions that exists for a multiverse setting as well.
Yeah, something like that. Yeah. Would that
So
be the right understanding? Because I really want to get this correct.
yeah, I think so there's a couple of ways to think about this. So let me just say the in principle claim is that there would be, they could, so the in principle claims there could be, right, a problem of initial conditions, even in the multiverse setting, which is going to relate to the kinds of conditions that arise or are necessary to give rise to a multiverse in the first place, right? So if there's some higher energy theory that's not, say, string theory, which is, or the theory that's parameterless, there will be parameters, and you could always point to them and say, well, why did you have to set them to be this? It may not be a legitimate question at that point, right? But you could still point to them and say, why do those parameters have to be this? And maybe there's an initial conditions problem waiting in the wings, right? Even if we solve it for now inflation. So there's another way to think about this whole state of affairs that I think is important to be clear about. And frankly, this way of thinking about things arose as a result of the debate that I was mentioning right at the beginning. And that is that you really do need to push inflation to energy scales which are higher than those that are involved in the imprinting of density differences in the early universe that account for the cosmic microwave background temperature differences. And so you could take the point of view that I'm not going to do that, right? You could take what is in effect an effective field theory point of view on inflation and about theories more generally. And you could say, what I'm really interested in is thinking about inflation as a theory, as it applies at the energy scales at which I know it applies, or at which I have good evidence that it applies, right? And I'm going to cut consideration. I'm going to put aside the issue of higher energy densities. So this separates, and therefore the multiverse, right? So from that point of view, you separate the problems. The other problem that's waiting in the wings, you can push aside, and you can just focus on the initial conditions problem for inflation. So I guess I just wanted to point out that there's a way to genuinely separate, and there's a formalism for separating the considerations. It's effective field theory of inflation formalism, which really does separate the considerations to a large degree, which one would want to be aware of, I think, in thinking about this problem. I think that, and let me say one final thing is that the larger problem here is there always an initial conditions problem? Are we ultimately striving for theories that, are somehow initial conditions less? Is that a legitimate thing to ask for? Are we always going to have to set down something? Are we always going to have to make a choice? This is always a question that's lurking in the background.
All right, thank you.
Okay, are there more questions out there? Otherwise, it's about time to, and it's 5 to 12, so it is about the time we would plan to kind of wrap up for the day. So any last question? Let's say thank you to whatever virtual way you can, I guess.
Thank you.
That was great.